Hello everybody, and welcome to my 36th video now. This is a practical demonstration. I'll be demonstrating the Quaternary SR and D type flip-flops. So first of all we have the SR flip-flop, and I've got a signal generator here which generates quaternary logic states. So here we have the S input to the SR flip-flop, 0, 3, 2, 1, 0, and the R input 0, 1, 2, 3, and I'm scoping the output with a voltmeter to indicate the voltage level, logic state level. So first we'll start with the set position, logic set 3 logic position. So S is a 3 and R is a 0, so we'll set S to 3. So S is a logic 3 here, and you can see here that the voltage is 4.92 volts, which is quaternary logic 3. So the idea is to get it to the hold state, which is 0, S equals 0, R equals 0. So now I'm going to do that. So S equals 0 and R equals 0. And you can see that the 4.92 volts is held. So that holds a quaternary logic 3. Now I'm going to set a quaternary logic 2. So I'm going to set R to 2 and S to 2, sorry, and R to 1. And you can see on the voltmeter that's 3.26, which is a quaternary logic 2, 3.26 volts. So the idea is to get it to the hold state 0, 0, S equals 0, R equals 0. So I'm going to put R equals 0 and S equals 0. So that's the hold state. So I'll try it again. S equals 2, R equals 1 is a logic 2. I'm going to set R to 0 first, then S to 0. So there we go. So we can see it's held the 3.27 volts, which is like I say, a quaternary logic 2. So now I'm going to set a quaternary logic 1, which is S equals 1 and R equals 2. And as you can see, the voltmeter's gone down to 1.63 volts, which is a quaternary logic 1. I'm going to set R to 0 and S to 0, S to 0 first, which is there, and R to 0 there. And you can see it's held the quaternary logic 1 there, 1.63 volts. So I'm going to do the same thing again, set R to 1 and S to 2. See, it's set on 1.63 volts, a quaternary logic 1. I'm going to set R to 2, R to 0 first, then S to 0, and it's held the logic 1. So next I'm going to set a quaternary logic 0. So S equals 0 and R equals 3. So I'm going to set R to 3, and you can see the voltmeter's gone down to a quaternary logic 0 volts. And all I have to do to get it to the hold state is to set R down to 0, which I've done there, R to 0, and it's held the quaternary logic 0. Right, I think that concludes the SR flip-flop. Next we'll have a look at the D flip-flop. Move this out of the way. Right. Let's connect this up a minute. All right. Right, so this is the D-type flip-flop with the quaternary successor gate wired from the output of the D to the input, then from the output of the successor gate into the D input of the D flip-flop. So you should get a counting up type of arrangement. So I've got to turn the power on. Right. So what I'm doing is scoping the clock, and it goes from a negative, starts at positive and goes to the negative edge. So the clock activates from a quaternary logic 1 to a quaternary logic 0, the negative edge of that. So I'm simulating that with this clock input here, and you can see the output Q goes from 0 to 1 to 2 to 3 and back to 0. So if I connect it to a clock signal, you can see the output cycles from 0, 1, 2, 3, 0, 1, 2, 3, and this is the clock signal I'll fit in here. So yes, so that is the D-type and the SR flip-flop. Right, I think that concludes the video. I'd just like to say I hope you've enjoyed it. Thanks for watching. Bye.